Introducing Redis, the database that developers love, with Simon Prickett.
Okay, thanks very much. Thanks for the intro and thanks for the opportunity to CFE. Susie's right, I do enjoy coffee today. I actually have a tea, but usually it's coffee earlier in the day. Okay, so I'm here to talk about Redis, and I'm going to assume that you've probably not seen or used it before, or maybe not seen or used it in a while and don't know what's been going on with it in the recent years or two. So as Sue said, I'm Simon. I'm what's called a senior curriculum engineer at Redis University. So I create content around Redis, and we provide online training courses. So first up, what is Redis? You could think of it as a database. So it's a data store. Some people call it a data structures server because it's not a traditional SQL-like database where you have tables and a SQL language to query it. Some people use it as a message broker, so you can use it for publish, subscribe. Some people use it for streaming data, and some people use it as a cache. So I like to think of it as essentially a server that provides sort of structured shared memory between different processes that can put things in there, get things out, and have behaviors associated with those things in there. So we'll look at what that means in a minute. But basically, we're going to look at Redis as mostly a key value data store today. And the other cool thing about Redis, or the interesting thing that's sometimes a misconception, is it's supremely fast because all the data is kept in memory all the time. So it's kept in RAM. It's not on a, well, it can be persisted to a disk, but all of your reads are going to come from RAM, which means that they're going to be extremely fast. One of the common misconceptions is that that means Redis isn't persistent. So if you pull the plug out of a machine where everything's in RAM, you've lost everything. The data can be persisted, and you have a lot of control over how that happens, and you can trade that off with that speed of access. But sort of takeaways are, it's a database. It works as a key value store. It does a lot of other things, and all the data is going to live in RAM. So where can we get Redis, and how much is it going to cost us? Well, the good news is it's open source, so it's free. So you can go to redis.io and build your own. You can get it from source, or you can get it from Docker if you want to run it that way. It's extremely popular. So there's been over 1 billion downloads of Redis from Docker Hub already. That figure's from quite a while ago now, so I would expect it to be substantially higher. And as is common with a lot of open source products, you can also get them on various cloud providers. So Redis Labs, where I work, provides a commercial version of Redis called Redis Enterprise that we host, and you can sign up for, and we'll make sure it stays up and you can just get on with using it. You can also get Redis from other cloud providers. So I said Redis was a key value store and a data structure server. So what does that actually mean? If you're familiar with other databases, so sort of MySQL or a Postgres type database, you'll be familiar with the relational model. So you put data into tables, you define schemas for those tables, they have fields, and each row in the table is like an item, and it has each of the fields populated if it's required, or null if it's not required. But every row will have the same schema, every table has a schema, and things live in tables. If you're familiar with something like MongoDB, you'll be used to storing documents, so say JSON or some sort of structure, and query those through paths through the document to different parts of your data. Redis is in the class of what's called key value data stores. So everything in Redis is stored at a key. So if you think of like a huge set of boxes, or a huge number of like mailboxes or pigeonholes, imagine every one of those has got a name, and you can put something in it. So to put something in it, you kind of go find it, look, note the name, put it in there. To get it back, you need that key to get it back. Where Redis differs from other key value stores, like say Memcache or, Memcache, is that the things that you put in have distinct types. So you can put in a plain string, which is quite a common use case. You might want to just remember hello world at a particular key and then get it back later. And there's nothing particularly fantastic about that. You can put stuff in, get stuff out. It works like you'd expect. Redis has these other data types that add extra behaviors. So the ones with the hearts here are the ones we're going to look at today. So those include hashes, which model something that looks like an object or an associative array. So inside a key, I could store something like a user record for me, and it would have fields like name, and the name would be Simon, and location would be San Diego, and my user ID would be whatever, and my email address would be something else. We're going to look at how those work. We also have a list data structure, so you can put things in a list and it will maintain essentially a doubly linked computer science style list of those, so it'll remember the order that you put them in. And we'll look at how you can use those for a queuing use case, but you could also build a stack out of that. We're going to look at sets. So a set models a mathematical set. So this is good for counting things or checking membership of things and deduplicating things. Because if you put something in a set multiple times, it's going to deduplicate it, as no duplicates are allowed. So if we added A to the set A, B, C, D, E up there, we'd still have A, B, C, D, E. But if we added F, we'd have a sixth member. And then finally, we're going to look at something called a hyperloglog, which is it's in a class of algorithms and data structures called probabilistic data structures. So hyperloglog's interesting. It's another way of counting things like a set, but it's not entirely accurate. And that sounds like a bad thing, but we'll look at why it's not a bad thing. So for each of these data types that Redis has, here's some example usages for them. The majority of you with Redis experience, I would imagine, have probably used number one, the string, to cache things. So Redis can be used as a cache. We'll look at how that works. That's traditionally been where Redis has found its way into enterprises and people's stacks, and maybe they haven't gone further into looking into the other things it can do. So we'll be looking at some of those other things like storing the hashes, using lists, sets, and so on. So this talk's going to look at like one use case for maybe 50% of the data structures. There are other things. So just quickly look at things we're not going to cover today. So you can use Redis to store geospatial information. So you could store like a load of information about where cars are for an Uber-like business in real time and keep updating those. And then you can ask it, find me all the cars within so many miles of a given location. And it's going to come back with, here they are, and here's the distances from that location. And this will be blazingly fast because all of this is in memory. So for powering like a real-time service like an Uber or anything that you need very, very quick retrieval on, and the data changes a lot, it's great for that. We also have things like sorted sets, which are used in a lot of gaming applications for scoreboards. So a set stores a set of members, so it might be like a bunch of usernames, and a sorted set stores a bunch of usernames with a score associated with them, and then you can order them by score. So if you were building like a real-time leaderboard for an online game, you could use it for that. So it's a bit of theory. How do we actually start using this data store? There's a couple of ways we can, well, 3 ways we can interact with it. There's some tooling. So if you build your own Redis or get it in the cloud, you'll find that there's a CLI. So you can type in commands. It's a bit like PSQL for Postgres. And you type in commands and it affects the state of the database. There's also a graphical tool that is free and runs in the browser, and we'll look at that as well. And that's called Redis Insight. And that allows you to look at the state of the database in a more sort of browsing way. So you can look at the keys, pick on a key, and it will render out what's in that key depending on what the content is. And you can manipulate it too. And then obviously, really, when we're using a database, we don't really want to be using CLI type tools. And we want to be doing something with a programming language. So for that, we need a driver or a client library for our programming language. And the good news is Redis has drivers for all of the popular programming languages. So we're going to look at Java, Python, and Node today. But if you're developing in Ruby, C, Rust, Go, Zig, C++, C#, a bunch of other languages, there will be one. And someone was asking, is there just the 10 data structures? Those are like the 10 core ones. And towards the end, we'll look at something called the modules API. And that allows you to extend Redis to do different and new things, either through your own code that you can write stuff with the modules API that adds commands and data types to Redis, or you can get those from providers who implement them. So Redis Labs, for example, builds a source available Redis JSON module, so you can add JSON documents as a native data structure in there. We're going to look at that for how to do some searching. So how do we do some very, very basic commands with the Redis CLI? Let's assume that we are modeling some sort of hotel problem, and we want to know who's in our rooms. So we're going to decide to call, have a key for each room, and we're going to have a key that says we're going to use the name occupant : room name. And generally, there's no strict way of naming Redis keys. You can use any string you like, but we generally try and encourage people to use some sort of schema in their strings so that it's easier to make these keys up, find them, search by them, and also just keep your database organized. So if you have multiple applications using the same database, they won't have a key name clash necessarily. So at the very top here, we can basically say to Redis, hey, does occupants : 101, does that key exist? And it says 0, no, it doesn't. So we can go ahead and set it. So we set occupant 101 to my name, and then we ask it, does it exist? And it says, yes, it does. And we can get it back again, and we get my name. So nothing spectacular there. Things to note, there was no setup step here. We didn't have to declare occupant 101 as a string key. We just put something in it. We didn't have to create something before we set it. It was created on set. Then down at the bottom, we can delete that key and check if it exists again. So very, very basic CRUD type operations on strings in the CLI. How does that map to a programming language? So here in Python, we simply import the Redis client for Python, which is, well, Redis. And then we declare a key name. So I've got it in a string there, and we reuse it a bunch of times. Line 5, I connect to Redis. I'm just using the default, so it will connect to Redis on my local machine, but I could specify a host and a port and a password if Redis happens to live somewhere else. And then at line 7, I'm starting to run Redis commands with the Python client. So the way a lot of the programming language interfaces to Redis works, and Python's a good example of this, is that you just call a function name that's named the same as the Redis command you want to use, and it generally takes the same parameters. So exist takes a key name. So there at line 7, I'm calling r.exist key name, and it will give me back 0 at this point. And then all the way down, I can set and get stuff. So what are we going to cover today? Because obviously just arbitrarily setting and getting stuff in Redis isn't very interesting from the perspective of what can I use this for? We are going to cover 4 different use cases. So first off, we're going to look at how to build a queue. And we're going to use a Redis list for that, and we'll do it in Python. We're going to look at 2 different ways of counting different things and why that might be useful, and why there's 2 different ways and why that might be a good idea. We're then going to third look at caching data with Redis and strings, which is probably what most people have used it for, which is also why I didn't want to do it first, because I see some new things first. And then last, we're going to look at how we can do a faceted search type operation over data in Redis, which is unusual for a key value data store because they're not known for having that ability generally. I'm going to do each of these examples in a different language, but the choice of language is completely arbitrary. The Redis clients for all of these languages support all of these things. So we could have done any of these demos in any of these languages or others. If I knew C# better, I could have done one in C# or Ruby. So first up, we're going to have a look at lists. I'm going to have a look at building a queue with a list. Why might we want to build a queue? We might have 2 different processes or microservices or different parts of our application that are linked to each other, but don't necessarily work at the same rate. So we might have something that kicks out jobs or packages of work that need to be done much, much faster than the thing that can do them is able to do them. In which case we kind of need a queue or a buffer between the two of them. And a list is a good way of doing this because it preserves order. So here's a diagram of basically a double linked list from computer science class. So you'll see that the list has a head, it has some elements, and each of those elements is linked to the previous and the next element. So we can traverse the list. We can also get the thing at the head. We can get the thing at the tail. Putting this into more context, how is this useful to us? So imagine we're still a hotel and we've got a housekeeping system. So imagine we have like two different processes here. We have what's generally in systems terms called a producer process. It's putting things on the queue. And we have one or more consumer processes that are taking things off of the queue. So we're going to use the Redis list to model the queue here, and we're going to use a couple of different Redis commands for that. So what we're going to put on our queue is a JSON object that represents a job that needs doing in the hotel. So Redis lists support putting strings into each member of the list, so we can just stringify the JSON, put it in there, and then our consumer can get it back and read that object and see what needs doing. So the queue or the list, like everything else, has a key. So we're going to call our key just jobs in this case because it's jobs that need doing. How do we get something on the list? We use the lpush command or list push command. So we are going to use that and provide it with the key name and provide it with the JSON that we want to push onto the queue there. And it will push a job onto the queue, and the queue will then have one entry. So in this state, it's had 3 things already pushed onto it. Again, note that there's no setup or like schema definition process here. The way that we create a list is the key name is we just push something onto that key name, and then Redis says, oh, okay, you want a list there, and goes away and does whatever it needs to do to create a list at that point, pushes the first thing onto it. So if we then have a look at some code for this, I'm going to switch to VS Code here. So we have 2 different services operating here. So I have 2 Python files. I have a producer and a consumer. So let's see if we make this a bit bigger. My producer job here is pretty simple. We just have a string with the key in because we're going to use it a few times. I've got a Python list with some random jobs that need doing. So housekeeping understands things like cleaning, room service, taxis, and so on. I connect to Redis. I'm going to delete anything that was at that key before just to make sure that that key is available to use. So delete the jobs key. Then I'm going to go into a loop forever and basically say I want to make a job, which is going to be a Python dictionary, and it's just going to have a random room number and a random one of those cleaning or room service things. I'm going to convert that to JSON stringify it, so I convert it to a string. And then I'm going to push it into Redis, so into the list. So what we see is I'm going to use the lpush command. We're going to have the list key, jobs, and the payload of that stringified object. And then basically this code is just going to sit there and go to sleep for a little while, and every now and then it's going to create a new job. So if I start running this, what we can expect to happen, let's start this up. So it's off. So it's started running, it's added a job, and when we add a job to a queue or we push something onto a list, Redis tells us how long the list is. So every time it adds one, it's telling us how long the list is. Obviously, multiple things could be pushing onto this list. So it might not always increase by 1. So let's just stop that for a second. So we've had this running now. So we want to see what's in Redis here. So I'm going to use the Redis Insight tool here, which is the graphical way of looking in the database. And I'm going to refresh it. And we have a key up here called jobs. And what we can see here is that this jobs key contains all of these things. So it's a list that contains all of these jobs that the producer put on there. So what we then need to do is, if I run our consumer, which we'll have a look at in a minute, that's going to go and start doing the jobs. So it's currently doing the first job, and there's a backlog of 4. It's doing the second one now. And if I refresh this, what we'll see here is that the number of jobs is disappearing from Redis as the queue gets shorter. So the consumer's pulling things off the list, and it's now finished. So it's checking for jobs, and there was nothing to do. So it's just going to periodically check there, and there'll be nothing to do. So if I refresh this now, we actually get what looks like an error. Something went wrong. So where I said creating a list, you just push the first thing onto the list and Redis creates it for you, it'll clean up after itself as well. So if we pull everything off of the list again, pop it all off of the list, then Redis will basically delete the list when it's empty, because there's no need to store anything there. So if I run the producer again, it'll recreate the job and it'll start doing it. So if I do duplicate this tab, and so the consumer's over there on the left, it's got nothing to do. And when I start the producer, it adds jobs to the queue, and then the consumer will take a look in the queue and go, oh, I need to do extra pillows to room 183, and then room 270 needs extra towels. So these are now talking to each other through Redis. It's the only way that they don't know anything about each other. We could start multiple of these consumers to catch up a backlog, and they don't know anything about the consumer. They just know that this key here exists in Redis, which it's still not going to have anything in it, because our consumer is working away as fast as it can. So if I stop the consumer there and let a backlog build up, you'll see that this key rebuilds. So there we go. We've got 2 jobs. And this is the only thing that they both know about. So how does our consumer work from a code perspective? It's also pretty simple. So again, we know about the key jobs. That is the Redis key that we want to talk to. It's got a list. We connect to Redis, and then we go into an infinite loop. And I'm using a feature of most Redis clients here that allow us to send multiple commands to Redis in one network round trip. So if we want to send multiple commands, we start a pipeline, and then we send a couple of commands. So I'm basically saying the br pop command is get the thing off the tail of the list and block for a period of time if there's nothing there. So it'll wait for like 5 seconds, and if nothing's there, it'll just give up. And if something's there, it'll pop it immediately. So it gets the value off of the list. That's a string. And then we're asking it how long's the list afterwards in that pipeline. And we're sending this to Redis and say, hey, do both of these commands. So when we get the results back, we have a look at the first result in the resulting list is going to be this br pop command. So it'll be nothing because there was nothing in the queue, or it'll be a job. And the second one will be the number of jobs that are remaining in the queue, so the length of the list. And then all we do is just print those out, and then this one goes to sleep for a little while, goes back to the top of the loop and checks Redis again to see if anything's there. So this is sort of polling, but it's using the blocking feature here in Redis, so we can block for an amount of time. And I could implement like a decaying retry here to say if there's nothing to do, wait 10 seconds next time. If there's nothing to do, wait 20 seconds. And then after so long, just give up trying, because maybe housekeeping is never going to make any jobs anymore. So someone was asking, is there concurrency management supporting multiple producers and consumers? we can run multiple of these at the same time because Redis is single-threaded. So basically, they can't compete with each other for server resources. If I send a command and another client sends a command, they'll get done in an order. So I could start here. Well, actually, we've been running the producer for a while, so we have 38 jobs in the queue. So we have 38 jobs there. Look here. There's a lot of jobs here. So we need probably to put more people on house cleaning. So if I run one consumer here and I run one consumer here, they're both going to talk to Redis and they're going to get different jobs because when they connect to the list, one of them's pop command is going to be executed. They'll get a job back, and then the next ones will be, and so on. So between them, these two will now work together and drain down that queue. So we've got jobs getting done faster than they would have. Somebody else asked, does the streaming work differently from lists in Redis? Yeah, you can implement a queue with what's called a Redis stream, which is the most complicated data type. Beyond the scope of this talk, as it's like a whole 4-week course on its own. But if you're familiar with using something like Kafka and or you want a timestamped append-only log, then Redis streams is a good way of implementing queuing type behavior. It also has blocking read operations. It also supports the ability for consumers to hold on to a job and say, I'm doing this job, and if you don't positively hear that I've done it in a little while, assume that I've crashed, and then your application can reassign it to another worker. So Redis can help you with that sort of stuff using the more complicated streams type. For a lot of cases where you just want a buffer, the list is great. But if you wanted streams with like multiple concurrent consumers that have to work in groups to do very, very different things, then the stream type is good. Streams was introduced in Redis 5 a couple of years ago, so it's one of the newer data types. So we'll just stop this. So basically, we can implement a queue with a Redis list. If we wanted to, we could also implement a stack because the lists are sort of double-ended. I can do both operations on both ends. So if we move that consumer from the right-hand side to the left-hand side and we used a command called lpop or blpop, if we want to block and wait, then we have a stack. So stacks are good for reversing things. So if for some reason we wanted to put things in there and then get them back, so like page history or something like that, we could use the list as a stack. So moving on to our next use case, Redis is also really good for counting things, which on the face of it doesn't seem like too big a problem, right? You just have an integer or some sort of number in your programming language or your database, and you just add 1 to it when you see something. What we're talking about here is counting unique items. So for example, if you wanted to record all of the IP addresses that have viewed my web page today, or all of the vehicle license plates that have been past a particular camera on a street or entered a parking lot, then you can't just count, oh, this event happened, we'll increment the event count by 1. You have to actually look at the event and say, oh, has this event happened for this unique ID before? So has this license plate been past the camera, or has this IP address been to this URL? And there's a couple of ways you can do that. And there's 2 Redis data structures that support it. So there's a set, which is a mathematical set. And there's a hyperloglog, which is a probabilistic data structure. And there's trade-offs between the 2 of these. So we'll have a look at that. So just comparing sets with hyperloglogs for counting things. So let's look at the set first. One of the things we need to know is, as we're counting things and remembering them, the number of things and the size of the data structure gets bigger and bigger because we have to remember everything we've seen in order to know if the next thing is unique or not. So the good news here with this set is the ability to add to a set is big O of 1, which you may not be familiar with big O notation, but it describes the performance of an algorithm. So as the data set grows, adding to a set takes the same relative amount of time, is what we're saying here. So I can add something to a set with 2 items in it, take me about the same time as if the set has 10 million items in it, which is good for this use case because we don't want it to slow down as the set gets bigger. The other good news is that asking a set what its cardinality, which is a mathematical term for a number of items in it, is also a big O of 1. So we can say, hey, how many items are in this set that you've been keeping track of? And Redis can tell us 27, 4 million, whatever. And the cost of doing that is not proportional to the amount of data we're storing. So that's good. Sets are also really, really accurate. So if we store 500,000 unique things in a set and we ask it, how many unique things have you seen? What's your cardinality? It'd say 500,000. So it's going to be right. And that's important because if we're counting something like votes or we're counting something that we really, really care about the accuracy of, we want that. But that comes at a cost. So if we are storing 500,000 things and each of those things has a finite size, then the size of our set in Redis is going to be 500,000 times the finite size of each thing, which could get very, very large. And as Redis keeps all the data in memory, that might be something that you need to consider. So if you want accurate, you're going to have like a space growth problem. The other advantages of sets are we can retrieve items from them and we can check their membership. So let me just quickly demonstrate this. So if I go to the CLI here and I can use a command called add. So I'll add something to a set. I'll call it my set and I'll add a member called, we'll store names. So Simon, Dave, Mohammed, and Jules. So a couple of things is I've just created a set in Redis with those 4 things in. So it tells me I created 4 things. There was, again, no setup step. I just said, hey, I want to add something to a set at a key called my set. And the command's very addict, so I can add multiple things in one go. So I added all of those 4. In the browser view here, I can see my set now has these 4 things in it. So I'm able to see what's in the set, and we can see how many there are. So from the CLI, we could do that through commands such as my set, what's cardinality in my set? 4, we've counted 4 things. S is member, my set, Simon, am I in the set? Oops, can't spell. Here we go, am I in the set? Yes, I am. Is Fred in the set? No, Fred's not in the set. And we can also say S members, my set. And we can get back everything we've put in the set, which is great. So on the face of it, set's very, very good for counting things. So what's the problem and why do we maybe want to use this other data structure, the hyperloglog? So the hyperloglog is a probabilistic data structure, which means it approximates things. So sometimes it's going to be wrong or slightly out, but there's a trade-off here. So good news with hyperloglog is adding and cardinality. So put something in one and how many things have you seen that are unique are also big O of 1. So no problem as the data set grows. We're matching the set for now. Accuracy, however, can be a little bit off. So there's a standard error in the Redis implementation there of 0.81%, which means it's going to be slightly wrong sometimes. And the win here because of that is the storage requirement. So hyperloglogs don't store the actual data, they store a hash of the data. And this keeps the size down. It doesn't mean that we get hash collisions. If you're familiar with hashing algorithms, there's going to be collisions and you can tune the algorithm for those, but we've basically accepted that that's okay sometimes. And we can't retrieve the items or check membership in there. So I can't say, hey, is Simon in the hyperloglog? Because it's been hashed and it's a one-way thing and I can't get that. But the big benefit is I could count billions and billions of unique items with a reasonable amount of accuracy. I'm only going to use 12K, which is good from the point of view of keeping your data in memory. And it's also acceptable for a lot of use cases. So if you imagine, for example, like Instagram likes on a photo or something like that, the absolute number of likes doesn't really matter. And storing it would potentially take a lot of space if you use the set to work out, is this new liker someone who's not liked this thing before? But with a hyperlog, you're at 12K, and you're going to be at 12K no matter what you put in there. So we have a look at some code for this. So to count unique things, we have a large JSON file of unique things. So here's some IDs that I created using an ID generator. There's 500,000 of them. And then we have some Node.js code that's going to basically read that file, and it's going to do two things. It's going to use two keys in Redis, one called HLL demo and one called set demo. And it's going to read them into Redis and put them into both a hyperlog and a set. So we will batch them up into, this code batches them up into 50s, but that's not really that important. And then it pushes them into the set there with the sadd command. It will then also push them into a hyperlog with a pf_add command. The reason why Redis commands for hyperlog begin pf is those were the initials of the person that invented the algorithm. And basically, it's going to do that for all 500,000 of the IDs. And then we're going to run some further Redis commands. We're going to say, hey, pf count, tell me how many are in the hyperlog. We're going to say scard, tell me what's cardinality of the set. We would expect the set to be 500,000 because it's accurate. And we would expect the hyperlog to be somewhere in the right ballpark, but not maybe right. Then we're going to look at how much memory each of those data structures is using in Redis. So we can see what the cost benefits of our trade-offs are. So if I take this guy down and if I run this, what we'll see is it's off and it's run and it's put lots of things in Redis, and we'll have a look at those. So it says that the hyperlog counted 498,384 unique items. So not perfect because there were 500,000 and the set got that right. But if we look at the memory difference, the hyperlog is using 12K to remember this, and the set is using something like 23 megabytes of memory. So the trade-off here is that set accurate, but hyperlog a lot more space efficient. If we go look at what that looks like in the browser here, we should have these two keys. So we have set demo, and in here I can see all of those values and I can still interact with them, and that might be useful in some use cases. Here for the hyperlog, they've all been hashed. I can't see anything or do anything with them. This is also potentially a good security thing, because if you were just counting unique license plates, but you didn't want to track people as they went through your camera, this is a decent way of getting an approximation of how many cars drive down the street, for example. So here in Insight, we can see that the hyperlog's taken up 12K of Redis memory, which is RAM, remember, because all the data lives in RAM. And the set, to get that accuracy, comes with a penalty if we've used 23 megabytes. So there's two different ways of counting things here, and you can kind of use either or both according to your need. And the good thing is the API, if you like, for them is basically the same. So these two commands are the same. We could swap pf_add and sadd around and the parameters stay the same. So you can move between a hyperlog and a set implementation of something that's counting something fairly easily. So third use case here is data caching. So this is the one that almost everybody who uses Redis will have seen Redis for. It's kind of what Redis is used for a lot, and it's built into a lot of other frameworks. So quite often, if you're using a framework like Express or Spring or I don't know, any of the other ones, Flask, there'll be a caching plugin for it. And underneath, if you dig in somewhere, the cache implementation will be Redis. There's one for WordPress. There's one for all sorts of things. So what's a cache and why would we use it? A cache is basically a way of being lazy or saving yourself money by, if I've done some work before, and I know that the next time I'm asked to do some work, I'll get the same result, I might as well remember what the result was rather than recalculate it every single time. So if I'm fetching like data from a URL or a web page, I might want to cache that for a little while. So store it in somewhere that's very fast and doesn't take any compute to recreate, so that when I get another request for that same thing, I can just go, sure, here's the one from the cache. And then over time, I would let that expire. It would be one way of doing caching, so that eventually that's not in the cache. And then I have to go get it from the backend database or whatever system originally generated it. Or if it's complicated math, I have to do the math again. So that's kind of caching. So what we're going to look at here is an implementation of caching where we have an application and it's calling a third-party API. So imagine my application needs to get exchange rates for a variety of currencies. So I'm going to use an API that's out there on the internet to do that. It's going to return a JSON document. And one way I could do this was every time my application needs the latest currency rates, I just go call the API and the API server responds. And that might be fine because they're probably scaled to do that. They probably have caching implemented themselves. But it's probably not a good idea for me to be doing this because a couple of reasons. If I want the latest stock prices or currency stuff, it's probably time critical and very time critical. So I want it as fast as possible. And also I might be buying this API as a service. So I might have a number of calls per day, after which I get charged, or I get charged more money for making those calls. Or I might be rate limited by that third party. So I can only call it so many times a minute. So if my service got really, really busy and it wanted the latest currency rates all the time, and I was doing this, I would be hammering them, and I would start to look like some sort of denial of service attack on their service, or they would start to invoke my rate limit, or I would get a very large bill. So what we're going to look at is putting Redis in the way to speed up frequently requested information, or speed up the retrieval of it, save us money by not calling that API all the time, and not hitting their rate limits, and just having that information in a data store that's close to the application, which is kind of useful. So rather than just, hey, I'm going to request the origin server make a call across the internet to that API server every time, what I'm going to do now is I'm going to say, hey, Redis, have you got whatever key we're caching the thing in? So if it's an API, we might cache it by the URL that we're requesting it in, because that's a unique thing. So why not use it as the cache key? And if Redis says, no, I don't have that, then we'll go and get it from the actual API. We'll incur an API hit and a network trip, and then we'll put it in Redis at that key, so that next time when we come to get it, we'll have it there. But it's going to go stale and get old quite quickly. So we don't want to do that, store it in Redis forever. So Redis keys can be expired. So all data types, and we'll show it with a string here, their keys can be expired. So you can say to Redis, after so many seconds, essentially delete this key, pretend it doesn't exist, get rid of it. This is great for caching because we can set something in Redis and then we can set an expiry on it and say, okay, let's store this for like 30 seconds, 60 seconds, half a day or whatever, and then delete it. And in this workflow, what will happen is if it's in Redis, we'll get it and we'll get a reasonably up-to-date one that's like 30 seconds or less old. And if it isn't, we'll go to the application API server, get a new one, store it in Redis and say, hey, hang on to that for like the next 60 seconds for me. And then subsequent requests will be cached from there. This is such a common pattern in Redis that the two commands at the bottom, set the key to a value and expire the key after so many seconds, also have a single command that does both. So we can say set EX, so set and expire some key after so many seconds to some value. So we're going to look at that with a, as I said, a currency API. So if we have a look at exchange rates API over here, this is the document we're going to cache. So their API is just a JSON document. It doesn't require a API key or anything, which means they do rate limiters and they do want you to cache. So let's have a look at how we're going to do that. and I'm going to do it in Java. So here we've got, Java's quite verbose, so I'll use the full width. So here we've got a really basic Java application. We're going to cache something for 15 seconds. This is just boilerplate code that all it does is it goes to a URL. So it goes to api-exchange-rate.io/whatever date we give it and a base currency that we want the values compared to. It'll get the JSON document from there and return it as a string. We don't really care about that. And then what our code is going to do to implement the caching is we are going to create a cache key. So I'm just going to use rates, colon, and then the date, and then colon the base currency. So like rates, colon, latest, colon, USD for dollars. And we're going to time how long this takes. So we'll start some timing software. We'll connect to Redis with Redis, which is the Java client for Redis. And like all the other clients, it basically wraps all the commands. So we're going to say, hey, Redis, get the cache key. Do you have this already? If we don't, then we need to go out and get it across the network. So we'll call that function that gets it across the network. And then once we've got it, we'll use the setex command and we'll store it in Redis and say, keep it around for that many seconds, which was 15. Store the document we got back and use cache key. So that's the case where we have a cache miss. If we had a cache hit, then there's literally nothing else to do because we've already got the document and it's good enough. And then we'll just print how long it took at the end. So for comparison, if we go and run this, first time we run it, it's taken 534 milliseconds and it's got it from the origin server. So if I run it again quickly, it's taken a mere 47 milliseconds because now we didn't go across the internet. We didn't get the document back. We didn't put it in Redis. We just said, hey, Redis, give me that document. And it went, sure, I have that. But I've probably been talking long enough now that 15 seconds has passed. So if we do this, you'll see we're back to slow again. So we're back to 446 milliseconds because Redis has expired it. If I run it again, 60, it's fast, it's not expired yet. And then let's just let it expire one more time and we'll look at what that looks like in the database. All right, so it's got it from the source. We've now got like 15 seconds to switch to Redis Insight here and find, here's our key, rates, latest GPP, here's our document. And you can see here, up here, it's got a TTL or time to live. So it's got 5 seconds left. And then Redis will automatically expire it and consider it old. So if I refresh it here, something went wrong because it's expired. That key doesn't exist anymore. If I refresh the keys list down here, key's gone. So that's one way that you can implement a cache. There are lots of other cache strategies. Somebody asked, does the key size matter? Yeah, it does, because everything you store in Redis is going to live in RAM. So if you have really big key names, then they're going to take up memory. So you should either store the unique part of the URL or some ID that makes that URL unique and not the whole domain and HTTPS and that sort of thing. In a simple application, you could do that. In something that's more complicated or is going to get used a lot, you want to keep your key sizes down, but also meaningful so that you can remember what's in them and that your application code makes sense. Because there's no schema in the database, the schema is in your application. So those names are going to be built by string concatenation or some other process in your application. It'd be nice to keep them semi-meaningful so that they make sense. So that's kind of a caching approach. Finally, we're going to have a look at what's called Redis hashes, and we're going to have a look at how we can solve what's perceived to be a problem with key value databases, which is everything we've done so far. I've always said, oh, we'll go and get this at the key, or we'll do this at the key, or we'll retrieve this from the key. But what happens if the data that we want is like in a set or it's in something else and it doesn't have a key and we want to find that? Or what if we want to do complicated queries? So in SQL, we can do things like, select star from users where age is greater than 10 and age is less than 25. That's kind of hard to do in a key value store. So there are extensions to Redis called modules And one of those is called Redis search, and that can help us with this. But first we need to look at a Redis hash, which is a data structure that models an associative array or a dictionary if you're familiar with Python. The hash lives at a key, so we're going to model animals that need adopting. We're an animal rescue in this case. So at the key adoptables :1001, which is the animal ID that I've arbitrarily given it, we can then set some name value pairs inside there. So we'll create a dog, and his name's Charlie, and his species dog, and his age is 13. And that's kind of our schema for these hashes, but Redis isn't going to enforce that. Adoptables 1002 happens to have the same key names, but Luna is a cat. But we could add key name value pairs to either of these, and we don't have to add them to the others. There's no requirement for all of these to match up. So the way that we create and manipulate hashes is using H commands. They all begin H for hash. So we can do hgetAll adoptables 1001, and it'll return all of the name value pairs. We can get an individual field, so adoptables 1001 name, just return the name. We can get multiple individual fields, and we can set things. So we are basically going to be working with data structures that look a bit like this, and we'll actually have a look at some in the database in a second. And the fun here comes with, okay, if we wanted to build like a website that allows people to adopt these pets, and we've keyed them by adoptables user ID, or sorry, adoptables pet ID, which is like a unique animal number across all time in our rescue, then how are people going to be able to do things like, well, I heard you had this cat called Luna, I need to search for Luna, or I only want to look at cats, or I'm only interested in animals that are between 7 and 11. We can't retrieve these values from Redis without knowing the key, and 1002 isn't part of any of that. So luckily, Redis can be extended by modules. There are other ways of solving this problem within Redis that involve different data structures, but we're going to look at this way. The modules basically are written in C, and they're plugin libraries that sit on the Redis server, and they can add commands and also data types. So Redis search is a module that basically adds search, querying, and full text search over Redis hashes, so over these sort of structures. So it's going to help us answer these sorts of queries. And it's also going to maintain that index for us. So as we add or change hashes, it'll see that happen in the database. It'll update the index. And then when we make queries against it, those queries will reflect the new state of the database. So if I go to here, I'm going to do this one in Python, but again, it's completely arbitrary language choice. So we've got a lot of animals as Redis commands here. So we're creating a lot of hashes. So animals have got a bunch of properties. So name, species, sex, fee for adoption, whether they're good with children or other animals, a location, because we can do geo searches, and a description for full text search. So I am going to load those into the database. And we will see what we get. So if we load all of those, we've got a load of data in the database, and we can see that now, hopefully. So when I refresh this, we should have a lot more keys. There we go. So we have all of these keys. If I randomly pick one, adoptable 938, we can now see what a hash looks like in the database. So it has all of these fields: children, sex, name, fee, the description, and so on. We can manipulate those fields here in Insight. I can delete individual ones, which we can do with Redis commands. I can expire this key, which would expire the whole class. It's a regular Redis data structure. But what I can't do is say, get me a dog named Cheddar like this, because there's no key here that would map to Cheddar. So what Redis search does is it allows us to create a search index over these hashes. So Redis search introduces some new commands. One of these is a create command. So I've created an index called adoptables. And I've said I want it to watch all hashes that begin with the key name adoptable : so Redis search is now watching everything that looks like that in the database that is a hash. And then I've basically said for each field in that, so this is the first time we've looked at any sort of schema with Redis data. So for each field, how to treat it for search perspective. So name, I've said text and sortable. Species, I've called it a tag because we want to search on exact values of cat or dog. Age, I've called a number, and so on. All the way down to location is a geo-searchable thing. So we can basically tell Redis search what some of these things in the hash look like, and it's okay for the hash to have other things or be missing these things. We're not imposing a fixed schema on the hashes. We're just saying these are the fields we want to search. And it will now maintain an index against those, and we can now write some better queries to get information about pets. So, sorry, wrong file. So if I then basically say I want to, Redis search has a client for Python, so I've imported that, and I tell it what index I want it to work on. So I created an index called adoptables. And now, without knowing anything about the keys in Redis, I can ask questions like, find me something called Luna, and like what field that's in the hash, we don't care. It's just essentially doing a search over the index for Luna, which is one of the pets. I can also then say to it things like, find me everything where the species field is equal to dog and the age field is between 9 and 15. So this is essentially like select star from pets where species equals dog and age is greater than or equal to 9 and age is less than or equal to 15. And obviously we can then write more and more complex queries. So I can say, find me all the cats that are good with children and the description does not contain anxious or nervous. And I can also say, find me all the dogs that are males and are within 50 miles of a location that I've specified, because we have a location field in there. So Redis search is also geo-aware. And then I simply basically just call these search functions from the client. I get a dict back, and then I just go over the matching documents, and I can print out anything I want about the pets. So the name fields from the hash, the species field, and so on. So if I run this really quickly, query index. So we ran a query to start with for anything called, or any match on Luna anywhere. So we got Luna, who is a cat. We wouldn't have been able to do that without Redis search because we don't know. We'd have had to have known Luna's animal ID to figure that one out. So let's try running one of the more complicated ones. So let's try find cats that are good with children. So we'll just change this here. And two things to note is, number one, it obviously found them. And number two, this is really fast because all of this is happening in memory. The index is in memory. The data is in memory. It's being persisted back to disk for recovery purposes, but all of this is happening in memory. So it's very, very, very fast indexing and query solution. So if you've got a data set where the data changes quickly and you want to index it, this is a really good option. So here we found 27 cats that are whatever the criteria was, good with children, so not anxious or nervous. So we can expect none of these explanations to contain anxious or nervous. We can configure Redis search to do synonyms. So we could set up a bunch of synonyms for those words and it would figure that out for us as well. And the syntax for this is then a very, very simple faceted search like thing, which is not something that you'd expect from a key value data store. And that was what I have for you today. So hopefully we've learned a little bit about key value data stores, caching, the value of having behaviors. So the ability to like add to a set and ask how many things are in a set and move things around in a list in a database. So we don't have to build all of that into our application. We've thought a little bit about trade-offs in database usage. So if you want fast, you need RAM. If you want fast, you sometimes have to give up some accuracy when you say counting things. And we've looked at how you might do something that this class of product is not traditionally known for, which is full text search, secondary indexing, and querying, which is, again, blazingly fast because Redis is entirely in memory, or at least all the reads are. So very quickly, if you're interested in learning more, we have university.redislabs.com. All of these courses are free. They all start on Tuesday again, and you have 6 weeks to do them all in your own time. We have some for programming languages, so Java, JavaScript, and Python, and then some for, somebody asked about Redis streams, which is a complicated data type. We have a 4-week course on that you can join and do for free. All of these courses relate to the open source product. So there's no tie-in to where you use your Redis once you take them. Obviously, we'd love you to use Redis Labs, Redis, but all Redis awareness is good. And that was it.
Thanks for watching.